students. My name is Prem Kumar. Today we are going to discuss fluorimetry. So in that we will discuss principle and theory. So here we are going to discuss the following contents. So overall fluorimetry will discuss principle, the factor affecting fluorescence intensity, instrumentation and application. So in this lecture, we are going to discuss principle and factors affecting fluorescence intensity. So coming to a basic introduction of fluorimetry. So in that fluorimetry, we are going to discuss first fluorescence and then fluorimetry. So fluorescence, it is a phenomena of emission of radiation when the molecules are excited by radiation at a certain wavelength. So fluorimetry, it is a measurement of fluorescence intensity at a particular wavelength with the help of a filter fluorimetry or spectrophlorimeter. So coming to principle, each and every molecule contains three types of electrons: sigma electrons, pi electrons and non-bonding electrons. The electrons may be present in a bonding molecular orbital. It is called a highest occupied molecule orbital. If it is in bonding, then we can say highest occupied molecular orbital, that is HO, we can simplify it. It has least energy and more stable. So whereas when the molecule absorbs radiant energy from a light source, the bonding electrons may be promoted to anti-bonding molecular orbitals, that is LU-MO. So in this stage, it has more energy and has less stable. Simple, we can say HO-MO is ground state and LU-MO is excited state. The process of promotion of electrons from HO-MO to LU-MO, that is ground state to excited state, with absorption of energy is called as excitation. So in the excitation, we have four different states we can absorb. In that singlet state, doublet state, triplet state, and then singlet excited state. The first one is singlet state. In this state, all electrons in a molecule are paired. So having this arrangement, so one arrow is up or one arrow is down, that means the pair. In doublet state, a state in which the unpaired electrons is present. Either they move upward and they move downward. Then triplet state, at a state in which unpaired electrons of same spin present, either positive or negative, like clockwise or anticlockwise. In singlet excited state, in this state, the electrons of unpaired but of opposite spin, like unpaired and opposite spin. So whereas in singlet state, both are paired and opposite spins are present. In doublet state, both are unpaired and having either clockwise or anticlockwise spin rotation. In triplet state, either having same spin present, either clockwise or anticlockwise. In singlet excited state, it contains unpaired in nature and having opposite spins, either clockwise or anticlockwise. When a light of appropriate wavelength is absorbed by a molecule, the electrons are promoted from the singlet ground state to singlet excited state. That means paired state to unpaired state. Once the molecule is in this excited state, relaxation can occur via several processes. So that relaxation, we can say simply emission. So for example, by emission of radiation, here I mentioned three different processes. in which the relaxation may takes place. And that first one, collision deactivation, second one fluorescence, third one phosphorescence. So this is the diagram, or we can say Jablonski energy diagram. So in this diagram, so we can observe all the process of emissions. Like here, so this is the ground state. From ground state to it moves singlet state S1, and from the S1 it moves to the S2 excited singlet states. So this will happen when the absorption takes place. So here the yellow color, it should mentions the vibration relaxations. So in this vibration relaxation we can say collisional deactivation. So in this there is no energy released, we cannot absorb any energy, and after that it converts to internal conversion. So from here the emission of radiation maybe takes place with a sort of some energy. So here I mentioned different colors. So red color indicates the fluorescence property. So it should be observed 10 to the power of -9 to 10 to the power minus second. Okay, in this we can observe light for a certain time, and here so violet is there, and intersystem crossing should be there, blue line. Okay, in violet indicates the quenching effect is one of the factor. From here, so delayed fluorescence may causes phosphorescence. Okay, so in fluorescence we should observe a radiative process, means radiative relaxation. In delayed fluorescence we cannot observe radiative process, so it should be non-radiative relaxation. So in this state the electrons having triplet state, and here we can observe phosphorescence. So phosphorescence here compared to fluorescence and phosphorescence, so we can observe phosphorescence compared to fluorescence some more time. So here, so I mentioned three process: collision deactivation, fluorescence and phosphorescence. So as mentioned in the diagram, so in which the entire energy lost due to collision deactivation and no radiation emitted. So complete energy lost but no radiation. So whereas in fluorescence the excited singlet state is highly unstable, then relaxation of electrons from excited singlet to singlet ground state with emission of light. So that light we can observe, so that is we can known as fluorescent property. And then phosphorescence at favorable conditions like low temperature and absence of oxygen, that is transition from excited singlet state to triplet state, so which is called as inner system crossing. The emission of radiation when electron undergoes transition from the triplet state to singlet ground state is called as phosphorescence. So here I mention some factors so which affects fluorescence intensity. So in that, concentration, quantum yield of fluorescence, intensity of incident light, absorption, oxygen, pH, and temperature and viscosity, photodecomposition, quenchers and scatters. So we'll see one by one. The first one is concentration. The fluorescent intensity is proportional to the concentration of substance only when the absorption is less than 0.02. So according to Beer-Lambert's law, the absorbance like our fluorescence should be directly proportional to the concentration of the sample. So A is equal to ABC. So where I0 gives the intensity of incident light, IT the intensity of transmitted light, small a for absorptivity of constant or molecular absorptivity, B for path length, and C for concentration. So where the absorptivity of constant should be constant value and path length is a fixed value. So therefore the absorbance or fluorescence of intensity is directly proportional to the concentration of the sample. The second one, quantum yield of fluorescence. The following equation may give the proper detailed information about the quantum yield of fluorescence. So eta is directly proportional to the number of photons emitted by number of photons absorbed. It is always less than 1.0. Since some energy is lost by radiation by less pathways like collisional reactivation process, intersystem crossing, vibrational crystallization. So in this type of radiation process, so we can observe quantum yield. Then third one, intensity of incident light. The increase in the intensity of incident light on the sample fluorescence intensity also increase. If the light intensity increase, automatically the fluorescence intensity also increases. Whereas absorption of sample solution in the container may leads to a serious problem. So adsorption if increase, so the decreasing fluorescence intensity takes place, and oxygen is also one of the factor. The oxidation of fluorescent species to non-fluorescent species, in that cases quenches fluorescent substance may be absorbed. Then pH. So alteration of pH of solution will have significant effect on fluorescence. For example, aniline in alkali medium gives visible fluorescence, but the same aniline in acidic condition gives fluorescence in visible region. Okay. So in alkali medium it gives visible fluorescence, and in acidic condition it gives fluorescence in visible region. Then temperature and viscosity. Temperature increases can increase the collisional deactivation and reducing fluorescent intensity. If collision deactivation takes place, so there is no emission of radiation takes place, thus there is no fluorescence. It means there is no effect on fluorescent intensity. If viscosity of solution is more, the frequency of collision are reduced and increase in the fluorescent intensity. Then photochemical decomposition. Absorption of intense radiation leads to photochemical decomposition of a fluorescent substance to less fluorescent or non-fluorescent substance. The quenchers, these are the very important factor which affects the fluorescent intensity. Quenching is the reduction of fluorescent intensity by the presence of substance in the sample other than the fluorescent analyte. So these substances are known as quenchers. The phenomena is known as quenching. So quenching is for having following types, that is inner fluorescence effect and self-quenching. In inner fluorescent effect, the absorption of incident light, that is UV, or emitted light by primary and secondary filters leads to a decrease in fluorescent intensity. By quenching, we should observe decreasing in fluorescent intensity. And then self-quenching. At low concentration, a linearity is observed. At high concentration of the substance, increase in the fluorescent intensity is observed. So this phenomena is called as self-quenching. So other than these two, we have another two, that is collision quenching and static quenching. So in collision quenching, collisions between the fluorescent substance and halide ions lead to the reduction in fluorescent intensity. Whereas in static quenching, it may be occurs because of complex formation between the fluorescent molecules and other molecules. So for example, caffeine reduces fluorescence of riboflavin. In this case, the caffeine is forming a complex with riboflavin moiety. Thus, the fluorescence of riboflavin automatically decreases. The last factor which affects the intensity, that is scatters. The scatter is mainly due to colloidal particles in a solution. Scattering of incidental light after passing through the sample leads to decrease in the fluorescence intensity. So this ends the principle and theory of fluorimetry. In next class, we will cover the instrumentation of fluorimetry as well as applications of fluorimetry. Thank you.